Hi friends, we have already learnt about the capacitors. Now you know capacitor C is equal to Q by V. We also learnt about the parallel plate capacitor and the formula is C is equal to epsilon naught A by D. Now today we are going to learn about combination of capacitors. So see the most common combinations used for capacitor are capacitors in series and capacitors in parallel. So first we are going to learn about capacitors in series. So when capacitors are said to be in series, if each capacitor acquire the same charge and the sum of the voltage drop across all the capacitor is equal to the total voltage of the battery. See, if you compare this with what you have learned in 10th standard about resistors, in case of resistor also you know that when the resistors are said to be in series, when the current remains the same and the voltage divides. So same thing is applicable here. In case of capacitor, the charges will remain the same. Again I repeat, in case of series combination, charges will remain the same, but the voltage will divide and the total voltage will be the sum of voltage drop across each capacitor. I hope you are clear. Now you can focus on this diagram. See, in case of the diagram, you can see that there are three capacitors C1, C2 and C3. But on each capacitor I have labeled the charge plus Q, and the total charge of the total voltage of the battery is V, and the voltage drop across C1 is V1, C2 is V2, C3 is V3. But you can see here in case of series combination the charges remains the same. The net voltage V will be equal to V1 plus V2 plus V3. What we are going to do is we are going to find the equivalent capacitance of all these capacitors when they are connected in series. So you can see in the diagram that the charges Q, 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 and the direction of current is from positive to negative, while the electrons will move in the opposite direction. So you can see here there is a plus charge Q and plus charge Q. In all three capacitors charges will remain same. That is how they are connected in series, and this is its equivalent diagram, that is the equivalent capacitance CS. That is what we will need to find. What is CS? This is the charge plus Q and this is the voltage V. So now we can say that voltage V, V1 is equal to Q by C1, V2 is equal to Q by C2 and V3 is equal to Q by C3. I hope you are clear, because already we had defined that Q is proportional to V and Q is equal to CV. So voltage across capacitor 1 will be Q by C1, V2 is equal to Q by C2 and V3 is equal to Q by C3. Right? Here the total voltage V is equal to Q by CS. Now in the diagram, if you see it more clearly, they have shown you the charges minus Q and plus Q. So while teaching the concept of capacitor, I had told you that when there is a plus charge Q, because of induction, on the other plate inner side there will be the opposite charge, and on the outer surface there will be the same charge as the first plate. Right? So this minus Q and this plus Q are just charges due to the induction. Again I repeat, this is charge Q on the first plate. On the inner surface of the second plate there is charge minus q due to induction, and on the outer surface there is charge plus q. Okay, so this plus q charge flows from first plate to the second plate. The q charge flow to first plate of the second capacitor, inducing the equal charges on both sides. So you can see here this plus q charge is flowing here. So on the first plate of second capacitor also there is a plus q charge. Again by the same process of induction, inner plate opposite charge, outer plate same charge. Though this again this plus q charge flows to this third plate, third capacitor. So the first plate of the third capacitor has plus q charge. Again because of induction minus q and plus q, and then this plus q charge is again coming back here. So this is how we can see that the total charge q remains same in case when capacitors are connected in series. Only the voltage are dividing. So we can write that V1 is equal to Q by C1, V2 is equal to Q by C2, V3 is equal to Q by C3. Let us go ahead. We know it, total voltage V is equal to V1 plus V2 plus V3. Let us substitute that values. So V is equal to Q by CS. V is equal to Q by CS, that I am substituting here. V1 is equal to Q by C1, V2 is equal to Q by C2, V3 is equal to Q by C3. Q common, take out it and cancel it. So 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. Remember it is just opposite to that of resistance. When resistors are in series, Rs, that is equivalent resistance, is equal to R1 plus R2 plus R3 and so on. Now when capacitors are in series, the equivalent capacitance, that is CS, so the relation is 1 by CS is equal to 1 by C1 plus 1 by C2 plus 1 by C3. If it is like that n capacitors, so in general you can write that if there are n capacitors, CS is equal to C by n. Because it is 1 by CS, this will become n by C. You invert them because it is a reciprocal, we want CS. So CS is equal to C by n. And you know it, if only two capacitors, 1 by CS is equal to 1 by C1 plus 1 by C2, C1 plus C2 upon C1 C2. So this is how you understood that when capacitors are connected in series, the charge on them remains the same while voltage divides. Now let us go to the capacitors when they are connected in parallel. When capacitors are connected in parallel, then what will happen? Then the voltage, the potential difference across each capacitor will remain same. But the total charges will divide, and the total charge will be equal to the sum of individual charges. Again I repeat, in parallel voltage, potential will remain the same, but the charges will divide. So now see this diagram. This is the diagram where capacitors, three capacitors are connected in parallel. You can see in the diagram the voltage of the battery is V. Across all three capacitors the voltage is going to remain V. But you can see this charge Q, it has divided into Q1, Q2 and Q3. Again as per our rule, the first plate has charge Q1, inner surface of the second plate by induction minus Q1, outer surface will be again Q1. This is Q2 charge. Here First plate Q2 charge, second plate inner surface minus Q2, outer surface plus Q2. Again same way for the third capacitor, first plate charge Q3, the inner surface of that will be minus Q3 and outer surface will be plus Q3. So you can add them Q1 plus Q2 plus Q3, again that all total will come out as Q, this will come out as Q, this will be Q, then this Q1, Q2 and Q3 will divide. So what formula we are going to use it? Let Q is the total charge and Q1, Q2 and Q3 are individual charges along the capacitors 1, 2 and 3. So Q is equal to Q1 plus Q2 plus Q3. But the total charge Q is equal to CV. So here we are writing the total charge Q is equal to CP, where CP is the net capacitance in parallel. But we know that Q1 is equal to C1. We now see here the voltage are remaining same. So Q1 is equal to C1V, Q2 is equal to C2V, Q3 is equal to C3V. All this when you substitute in this equation, this will become CPV and this will be C1V, C2V, C3V. If you substitute that values and if you take out the V common and we can cancel the V on both the sides, CPV is equal to C1V plus C2V plus C3V. VV will get cancelled. So in parallel, the equivalent capacitance is sum of individual capacitance. Again I repeat, in parallel the equivalent capacitance is sum of individual capacitance, that is Cp is equal to C1 plus C2 plus C3. If there are n number of capacitors in parallel, then this will be Cp will become n times C. So this is another important formula, that if there are n capacitors in parallel and each capacitance is C, then Cp is equal to Nc, the ratio of Cp by Cs, because Cp is equal to Nc and Cs is equal to C by N. Cc will get cancelled, is N square. For MCQ purpose this formula is very important. The ratio of capacitance in parallel to that of series means Cp by Cs. The ratio Cp by Cs is equal to N square. I hope all of you have understood. Now you can see here in this diagram there are n number of plates. So please understand it. If there are, you can see in the diagram, you can see in the diagram there are 5 plates. 1, 2, 3, 4, 5, 6. Sorry, there are 6 plates. But if you can see that the capacitors will be 5. So here the concept is, if there are n plates connected, like in example 1, 2, 3, 4, 5, 6, n plates are connected, right? Then there will be forming n minus 1 capacitors. Here 1, 2, 3, 4 and 5. There are 5 capacitors. You can see this, all this plus 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 is connected at the positive potential. All this negative 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 is connected at negative. So when there are n plates, they will be forming n minus 1 capacitors. This will be again helpful to you for solving the numericals. Next, today we'll complete the theory and next class we'll be going to do the numericals. So let us go ahead. Now we'll go for energy stored in capacitor. See, I told you in the beginning only, what is capacitor? It is nothing but the arrangement of two conductors separated by some dielectric. It is used to store the charge. It can also store the energy. This energy is electrostatic energy. So as seen in the diagram, you can see that there are two this is a parallel plate capacitor. There are two plates A and B. A is positively charged on plate B. Because of induction, there is a negative charge induced. Outer surface there will be a positive charge, but that we have done the earthing. I hope now this point is already clear to you. Now now understand this very carefully. Plate outer surface of the plate B is earthed, and C is the, let C be the capacitance. So the potential difference between A and B is V naught, because the plate A is insulated and it was charged to a potential which was initially V naught, and this is earthed, so there is no potential. So the potential difference between A and B is V naught, and let initially there is charge Q naught. Q naught be the initial charge on plate A. Now initially it was, now it is being charged. So when it is being charged, the positive charge, you can see in the diagram, the positive charge is transferred from negatively charged plate B to the positively charged plate A, and in doing so the work is done. Now see, understand this, as there is a potential difference, the charge will flow from higher potential to the lower potential. So here, as seen in the diagram, you can see that the positive charge is transferred from negatively charged plate, and the work is done in charging the plate A, and that work done is stored as the energy in the capacitor. So what is the amount of work done? So you know it, according to our definition, voltage is work done per unit charge. So let the small amount of work done, delta W, so that delta W is equal to V into dq. As seen in the diagram, you can see the small charge dq is getting transferred. So the work done, delta W is equal to V into dq, and V, you know, it is Q by C. So we are substituting that value. Now let us say that initially capacitor was not charged, so the charge is 0 and the maximum charge is Q naught. So the total work done is integration dW, and the limit of integrations will be from 0 to Q naught. Substitute the value of dW here. Value of dW is Q by C into dQ. 1 by C is constant. Integration Q, you know it, x raised to n plus 1 upon n plus 1. So integration Q raised to 1 is Q raised to 1 plus 1, Q raised to 2 by 2. So it will be Q square by 2. And when you substitute the limit, the work done will be Q naught square by 2C. So, and this work is done in the body as in the capacitor as electrostatic energy. And you know it, that work done is nothing but the energy. This is the potential, electrostatic potential energy. That is equal to Q naught square by 2C. But Q naught is equal to C into V naught. So C square and V naught, 1C will get cancelled, and you will get that energy is half CV square. So U is Q naught square by 2C, and you are substituting the value. So you can write it in any form. This is the most common form used is U is equal to Q naught square by 2C, means Q square by 2C, or U is equal to half CV square. In general, all three are one and same, just the different way of writing it. Half C V naught square, या Q naught square by 2C, or Q naught V naught by C. So depending whatever values are given, on that basis you have to find the potential energy stored in the capacitor is half CV square or Q square by 2C. I hope it is clear. Once again I am showing it to you that the derivation is very simple. The work done is potential V into dq, and V is equal to Q by C into dq. You are going to find the total work done, and that total work done will be stored in the capacitor as the electrostatic potential energy. So total work done is integration dw, and limits will be from 0 to Q naught, that is the maximum charge it has. Just you integrate it, 1 by C is constant, capacitance is constant, and Q dq, integration of Q is Q square by 2. Substitute the value, you are going to get as work done, and work done is nothing but the potential energy. So the electrostatic potential energy stored in capacitor is Q naught square by 2C, या half CV square. Let us go ahead now and we study about energy density in an electric field. This is not there in your textbook, but this is important. The same thing we are going to do it in case of magnetic field also. So guys, please understand it. The first, this is a new term, that is energy density. So what is energy density? So the energy density is nothing but the energy per unit volume. Again I repeat, see, in 11th standard you were learning number density. So number density is any number of electrons or whatever divided by volume or per unit volume. Here energy density is energy per unit volume. Now you know it that charge Q is equal to sigma into A. Charge Q is equal to sigma into A, where sigma is the surface charge density, and you substitute the value of electric field for any shape irregular. E is equal to sigma by epsilon naught. So instead of sigma you can write epsilon naught into A. Now we learned that energy is Q square by 2C. So we are going to substitute the value of Q square and 2C. Now this is in case of a parallel plate capacitor. So we know the formula for parallel plate capacitor is epsilon naught A by D. So when you simplify it, one epsilon naught will get cancelled. This will be E square A square, 1A will get cancelled. Denominator of denominator, D is in denominator of denominator, it will go in numerator. So in general you will get half epsilon naught E square A into D. This is area into distance is nothing but the volume. And when you divide this energy by volume, you get energy density. So energy density is half epsilon naught E square. This is very important. Again I repeat it. Q is total charge, sigma is surface charge density, A is area. So already we know this relation, Q is equal to sigma into A, and the electric field for any shape is sigma by epsilon naught. So we are replacing the value of sigma as E into epsilon naught. The energy, the formula for energy is Q square by 2C. This just now we learnt. The energy stored in parallel plate capacitor, U square by 2C. Now I am substituting the value of Q here, and substituting the value of capacitance of a parallel plate capacitor, that is epsilon naught A by D. When I simplify it, I am going to get it epsilon naught E square A into D. This A into D is area into distance, that is volume, and when you divide this energy by volume, you are going to get is half epsilon naught E square. This is the formula for energy density. Energy density is energy per unit volume. I hope it is clear. So you can see one important thing is that energy density is proportional to the square of electric field. E is the electric field intensity or strength of electric field. So energy density is proportional to the square of electric field. This is the another way you can do it by this also. Half CV square, put the value of C epsilon naught A by D, and V is equal to ED. This already I told you. In case of capacitor, E is equal to VD. Yeah, V is equal to ED. Simplify this, you are going to get the same thing, that energy density is half epsilon naught E square. I hope you have understood this. Now let us go ahead